Okay, so go ahead and what are your specific questions?
Numbers 3 and 21 on page 1107.
Okay. So here's number 3. In violet light with a wavelength of 400 nanometers, and I think they really mean 400 point.
Yeah.
Sufficiently energetic to break a carbon-carbon single bond. Oh, is it sufficiently energetic to break a carbon-carbon double bond? And it says the average carbon-carbon bond energy is 346 kilojoules per mole. So we have a carbon-carbon. The bond dissociation energy is 346 kilojoules per mole. And then we have violet light, which is 400, and we're going to call it 0.0 nanometers, okay?
All right.
So naturally, this is an energy, so you want to use this and convert it to an energy, right?
Yeah.
So how do we convert this to energy? Energy is equal to H nu, which is also Hc over lambda, right?
Yeah.
So we have 6.626 times 10 to the minus 34 joule seconds. Times, what's the speed of light? 2.998 times 10 to the 8th meters per second.
Yeah.
And we don't want to use 400 point nanometers. We're going to use 400 times 10 to the minus 9 meters. Okay, let's calculate this energy, and we can estimate the answer if we wanted to. 6.6 times 2.9 is 20. 20 divided by 400 is the same as 1 over 50. And here, negative 34 and 8 is going to be negative 26. When the 9 goes up top, that becomes a positive 9, so that becomes 17, right? Negative 17. And 1 over 50, we know that 1 over 5 is 0.2, so 1 over 50 is 0.02, which is 2 times 10 to the minus 2. So our answer should end up being 2 times 10 to the negative 19, thereabouts, right? Okay, so what, did you already plug everything into your calculator?
Yeah.
What'd you get?
I got 4.96 times 10 to the negative 19.
Oh, yeah. I'm sorry. It shouldn't be 1 over 5. It should be 1 over 2 and 1 over 20. My bad. Okay, so say that again. 4 point what?
The 97 if we're rounding.
Times 10 to the negative 19 joules, correct?
Yeah.
Now, that is the energy for what?
The wavelength of 400 nanometers.
Yes, but it's the energy of what?
1 photon.
Of 1 photon.
Yeah.
Well, we're not given the energy to break 1 bond. We're given the energy to break a mole of bonds. So is it fair to say that 1 photon will not break a mole of bonds?
Yeah.
Okay, but I think that what they're really asking is, will 1 photon break 1 bond?
So no.
Will this 1 photon break one of those bonds? So our dilemma is to either take this energy and turn it into a mole of photons, or take the bond dissociation energy and turn it into 1 bond instead of a mole of bonds. So let's do the energy and turn it into a mole of energy first, okay?
Okay.
So we've got 4.97 times 10 to the minus 19 joules. And then we're going to multiply by 1 mole, or excuse me,
Yeah. 1.
1 mole on the bottom and 6.022 times 10 to the 23rd on top. So this is per 1 photon. And this is that many photons per 1 mole of photons.
Yes.
Okay, so 4 times or 6 times 5 is 30, right?
Yeah.
And we're going to do one more thing with this. If we're done with this, we're going to get how many joules per mole, right?
Yeah.
But look at the number we have above. Is that joules per mole?
No, it's kilojoules.
So we're going to multiply by 1 kilojoule over 1,000 joules to see what we get. Now I can tell you already that this number is going to be kind of small compared to the number up above. And the way I'm doing that is, actually, I take it back. The number's going to be close to that. So 1,000 on the bottom is 10 to the third, right?
Yeah.
Put it on top and it becomes 10 to the minus 3. 10 to the minus 3 times 10 to the 23 is 10 to the 20, right? 10 to the 20 and 10 to the minus 19 is 10 to the 1. 6 times 5 is 30. 30 times 10 to the 1 is what?
30. Oh, 300.
300.
Yeah.
So we're going to say this is going to be about 300, which means it's not enough energy.
Okay.
So let's put the numbers in and see what we get. .97 second EE negative 19 times 6.022 second EE 23 and divided by 1,000. Oh, I have a syntax error. So I get 299 kilojoules per mole of photons.
Mhm.
Okay, so since that number is smaller than that number, it's not enough energy. And when we look at Vib Gyor, we know that Vib is around 400 nanometers. And what is red going to be around?
7.
700 nanometers.
Mhm.
Now, when we talk about this is going to be short wavelength and this is going to be long wavelength. When we talk about energy, what's the relationship?
Higher energy for shorter wavelength.
And this is going to be low energy, right? So if violet light isn't going to cut it, what kind of light is going to make this work?
Is it infrared?
No, infrared's over here.
UV then?
UV. So it takes stronger light to break bonds, which is UV. And you know what? When you think about it, we're bombarded with visible light all day long, right?
Yeah.
And if visible light would break carbon-carbon bonds, how would that bode for organisms?
Well, not well.
Not well. We would have to go outside and shade ourselves the whole time.
Right.
And not only shade ourselves, but shade ourselves from the reflection of light.
Yeah.
Either that or become a gooey mess because all their bonds are coming apart. So that actually makes sense when we think about it. Are you with me there?
Yeah.
Okay. So let's look at from the other aspect. Let's look at this and turn it into the energy for one bond. So in this case, we're going to multiply by 1 mole over 6.022 times 10 to the 23. And this is a mole of bonds. And we're also going to multiply by 1,000 joules over 1 kilojoule. So, how many times does 6 go into 346?
50 something.
I like it. 50 times, maybe a little more, right?
Yeah.
55? Okay, goes in 55 times. 55 times 1,000 is 55 times 10 to the third, right?
Yeah.
And then this 10 to the 23 makes that not 10 to the third, but 10 to the minus 20, right?
Yeah.
So we should get about 55 times 10 to the minus 20, which is also 5.5 times 10 to the minus 19.
Okay.
Okay. Now let's do the work. 346 times 1,000 divided by 6.022 second EE 23. And we get 5.75 times 10 to the minus 20. If I did this right. No, I didn't do it right.
Let me redo that.
Times 10 to the minus 19. I can tell by looking at my calculator what I did wrong is I multiplied by 100 instead of 1,000.
Oh, okay.
Okay, so that's joules per bond. So this is how much energy it takes to break a bond. This is how much energy we have from violet light. Is that enough energy to break that bond?
No.
Okay, so here it's kind of a different comparison in that this number ended up being bigger, whereas before it was the kind of the opposite. But here, that's not enough energy to break that bond.
Right.
So do you see that either way that we tackled this, we came up with the same result, that there's not enough energy?
Yeah.
And the take-home idea here is that you need to understand that for the bond association energy, they're talking about breaking a mole of bonds. Therefore, you need a mole of photons.
Not just
One photon can break one bond. That's the way it works. Just like only one electron gets ejected from a photocell when it gets hit by a photon, right? One electron per one photon.
Uh-huh.
Here's the same thing, one bond per one photon. Okay? All right. Good problem. Number 3. Now, you said there was another one. It was, which one?
21.
21. So 21 asks us to draw the structure of the chair form of cyclohexane. Identify axial and equatorial hydrogens in this drawing. Now, this isn't something that you will need to do on the exam, but it's certainly something you will need to do for organic chemistry. So if we draw a cyclohexane like this, these bond angles are too large. They're about 120 degrees. Now, each of these is sp3 hybridized, which means it's tetrahedral, which means the angles are 109.5.
But you just told me it was 120.
Well, if you draw it like this,
Flat.
like this, flat. So let me show you what I mean by flat. So I'm trying to get out 6 black spheres here because in this model, the black spheres are the carbons. So there we have 6 black spheres. And I'm going to bond them together into a ring of 6 carbons.
Going to make the bond strained, right?
I'm going to make this flat, like the drawing. Okay, so here's my 6 carbons. And when you look at it, you can see that it's kind of puckered, right?
Yeah.
And I'm going to flatten it out now. So I'm pressing down on all of the carbons so it's nice and flat. And now when I hold it up, you're going to see it's flat, right?
Mhm.
Now, if this is going to be stable, that means when I shake it, it should stay flat. And when I shake it, what happens is you can see that it's starting to pucker right there. You see that? Now, these angles are about 120 degrees. Now, what I'm going to do to make this more stable is I'm going to take this carbon and I'm going to raise it like that. And what you can see is that the angle is going to change a little bit. It's going to become smaller. And I'm going to take this and I'm going to push it down. And I have what's called the chair form. So can you see from the side that this is the head of the chair, this is the seat of the chair, this is the foot of the chair, like a recliner.
So we drew that yesterday, right?
We drew that yesterday. So the way I learned to draw it is looking at it from this side here or from this side here, it doesn't matter. But also, if we're looking at the side of the chair, I don't have the seat of the chair flat. I have the seat of the chair inclined. So that this carbon and this carbon are about at the same height, roughly. So, do you see how these 2 arms of the chair are parallel to one another?
Mhm.
So that's where I start. So here are the arms of the chair, and you see how they're parallel to one another.
Yeah.
And I end them and begin them in the same horizontal space. So if I drew from here to here, it'd be a straight line down.
Right.
Okay. Now, once you have this, I'd like to draw the head first. So I go like this and just pick a point and then draw that. And you'll notice that what usually ends up happening is this looks pretty much like a right angle, doesn't it?
Yeah.
And then here I go up to, do you see this distance here? Between these 2 lines? Do you see the distance between here and here is about the same?
Yeah.
Okay. So on this side, I'm going to draw a line that's like at a 90-degree angle. And it's going to be twice as long as this distance. And then I'm going to connect these 2. So that's our chair. Now, if we wish, we can put carbons in. Are you good with all the carbons?
Yeah.
Okay. Now we want to put in the axial and equatorial positions. So I'm going to show you a axial position. And actually, I will show you all 6 axial positions. So these are 3 of the axial positions. Do you see how the axial positions form a nice plane of hydrogens?
Yeah.
In the shape of a triangle when you look at it from the top. Now, if I show you the other axials, they are on the other side. So these are all axial carbons. And when you look at it from the side, you can see why it's called an axis now. If it were a wheel, these would be parallel to the axis of the wheel. So the axial positions are the easiest to draw. What you start here, you do is you start here at the head of the chair. And you draw a line that's straight up, and there's one of your hydrogens. And then you go to the left or to the right, it doesn't matter which. So I'm going to go down here, and you draw a line straight down. And then we draw another line that's straight up. Then you go to the next carbon straight down, and you go all the way around, changing the up down.
Okay. So
I'm going to
okay.
make this a little longer and do that and this and do that. And you see how these three hydrogens are basically all pointing in the same direction, parallel to one another?
Yeah.
Just like these three hydrogens are all pointing in the same direction and they're parallel to one another.
Okay.
So here I've skipped this guy. This has a hydrogen going down. And you see how these hydrogens are all parallel to one another, pointing in the same direction.
Yeah.
So we're going to put a little A next to these. What does the A stand for?
Axial.
Axial. Now we're going to put in the equatorials. Now I'm not going to show you the equatorials on the model. I'm just going to start drawing them in. We're going to start with this guy here.
Okay.
Now, when you draw the equatorials, you draw them opposite of the axials in the sense that if one is up, the other's down.
Okay.
So we're going to draw the axial down or the equatorial down, but it's not straight down. It kind of goes off to the left. And what we're going to do is, do you see this line right here? We're going to draw it parallel to that line. So there's an equatorial.
Okay.
Now this next carbon, we're going to draw this up. This is down, so we're going to draw the next one up. So we got to pick a line that we want to draw it parallel to. Do you see how this one looks pretty good?
Mm-hmm.
So there's your equatorial. So for this one, we got to draw one that goes down. What line do you want to draw it parallel to? If we draw it parallel to this, they run into each other, right?
Yeah.
But if we draw it parallel to this, that will look pretty good, doesn't it?
Yeah.
And this one is going to be parallel to this line right here. And do you see how this axial is down? And this equatorial is up. Now, up doesn't mean directly opposite. It just means up compared to down.
What line did you draw it parallel to?
Either of these two.
Oh, I see.
So basically the ones on the ends, you draw them parallel to the two lines you start with.
Okay.
And for these guys that are inside, you draw it parallel to the other line that goes to the foot. So this one's going to look like this. Do you see how this one is parallel to that?
Yeah.
And this last one, you're going to draw towards the head, and it's going to look like that. So this is really ugly looking. And this is often the way it's drawn. Without showing the hydrogens. So can you imagine the hydrogens at the end of those lines?
Yeah.
And this is a little cleaner looking than this, but this is basically it. And if you want to draw it the other way, you just do it like this. And again, straight up here, then down, then up, then down, then up, then down. And then parallel, 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 parallel. So here's the two chairs. Okay. And this is actually how glucose is shaped. You may have seen in a biology text where they show glucose like this with stuff hanging off of it.
Yeah.
Glucose is actually shaped like this, where there's that oxygen. Glucose is a chair. It's not. Okay. So that's number 21 and how to draw that. So what numbers were that? 3 and 21?
Yeah.
What would you like to do next?
I don't have any other specific questions.
Okay, then we'll do problems from that I have prepared from the back of the book. I think I have 26 more problems that I want to do. And we're not going to do them all at this setting.
Okay.
Okay, we'll just do maybe 4 or 5 at the most. It's already 11 o'clock. Okay, there are 7 possible dichloropropene isomers with a molecular formula C3H4Cl2. So dichloropropene isomers. Okay, draw their structures and name each isomer. And hint, don't overlook cis-trans isomers. So where do we start a problem like this? And the answer is we start with propene. So propene is going to be 3 carbons, and because of the ene, it's got to have a double bond. Now my preference is to put it on the left if I'm given a choice.
Okay.
So this is propene. Now we're going to have 7 of these. So I'm going to go ahead and draw 7 of these. This may be a mistake, but I don't know. Maybe it's not a mistake.
Why would it be?
So they all have to be like that. Now it says dichloro, which means we get to put chlorines on this. And the question is, well, where? Well, anywhere there would be a hydrogen. Because presumably if there was a hydrogen there in propene, you could replace it with chlorine by a reaction. So we have to put 2 chlorines on this. So that means once we replace a hydrogen with chlorine, we have to put another chlorine there that replaces another hydrogen. So my first inclination is to do this. Put them both on the same carbon if I can. Are there 2 hydrogens on this end carbon?
Yeah.
Yes, so I can do this. Are there hydrogens on this end carbon now?
No.
What is the formula for this? 3 carbons, 2 chlorines, how many hydrogens? 3 on the end and 1 in the middle for 4 hydrogens, right?
Right.
And the formula is supposed to be H4. So I automatically get a line drawing that fits the formula.
We have how many hydrogens?
4. 3 on the end,
Okay, I see.
3 on the right end, the right-hand end,
Yeah.
and 1 on the mountain peak.
Okay.
Okay, so this is where I like to start. Put them all on the left. And then what I like to do is this. I like to move one of the chlorines around. Keep one on the end and the other around. Move the other around.
Okay.
Now let's take a look at this first one. Oh, and here, I'm going to keep this on the end and I'm going to put the other one over here. Now that we have these drawn, I want you to convince yourself that the formula for each of these is C3H4Cl2. Take the time and convince yourself. And a really excellent way to convince yourself is you have a piece of scratch paper, you draw it out and draw in the atoms.
And
It doesn't
what?
get more convincing than that. Draw it on another piece of paper.
Yeah, you were cutting out.
And draw in the atoms.
Yeah.
And once you do that, you go, oh, there's 3 carbons, there's 4 hydrogens, and there's 2 chlorines. Done.
Yeah.
Okay. All right. So I've made 3 of them by keeping 1 chlorine on the first carbon and taking the other chlorine and moving it around, right?
Yeah.
Okay. Are any of these cis trans? So what are the rules for cis trans? 1, you have to have a double bond. 2, you have to have 2 hydrogens, 1 to each carbon of the double bond.
Mhm.
Does this first one have a double bond?
Yeah.
Does it have 2 hydrogens bonded to those carbons? No cis trans. Does this have a double bond?
Yeah.
Does it have 2 hydrogens bonded to that double bond?
Yeah.
Well, it certainly has one here, doesn't it?
Yeah.
Is there a hydrogen bonded there?
Oh, no.
No. So this does not have 2 hydrogens bonded to the double bond.
Right.
Does this have a double bond?
Yeah.
Does it have 2 hydrogens bonded to the double bond?
Yeah.
1 here going down and 1 here going up.
Yeah.
So what does that make that? Cis or trans?
Trans.
Trans. So let's draw the cis down here. So how am I going to draw the cis down here? I'm going to put the chlorine here. That one doesn't matter. But how do I make the hydrogens go in the same direction?
Put the hydrogen at the end of the double bond? No.
And put the chlorine going down, right?
Okay.
Because then the 2 hydrogens are both on the same side, right?
Yeah.
So this is the cis. Okay, so we have 4 of them right away. Now I'm going to put the chlorine here on the second carbon. One of the chlorines on the second carbon, and I'm going to put the second chlorine on the second carbon if I can. Can I put the second chlorine on the second carbon?
Yeah.
Well, if I did, wouldn't I have 5 bonds?
Yeah.
So I'm asking, can I do this? Can I put the second chlorine on the second carbon?
No.
No. So I'm going to put it on the third carbon.
Right.
Okay, does this have a cis or a trans?
No.
No, it doesn't, because there's only 2 hydrogens bonded to this, and they're both to the same carbon. So there's no cis trans. Okay, so now what am I going to do? I'm going to put the chlorine on the end carbon. And I need to put the other chlorine somewhere else on this. Where am I going to put it? If I put it here on the second carbon, haven't I already done that?
Yeah.
If I put it here on the first carbon, haven't I already done that?
About
So can I put it on the third carbon? Okay, now they say that there's 7 of these, right?
Yep.
Can you think of the 7th one? When we think about all the possibilities, here are the possibilities. You have a 1-1 for the chlorines. You could have a 1-2 for the chlorines and a 1-3 for the chlorines, right?
Yeah.
Just without looking at the double bonds and where they are. You could have a 1-1, a 1-2, and a 1-3. Or you could have a 2-2 and a 2-3. And the reason I don't have a 2-1 written down here is because I already have a 1-2. They're the same.
Yeah.
Okay.
How do you have a 2-2?
Pardon me?
How do you have a 2-2?
Well, I'm just saying all the possibilities without regard for how many chlorines you can put on there. So I'm don't worry about that. Just say 2-2 or 2-3. And we could also have a 3-3, right?
Yeah.
Okay. Now let's evaluate these possibilities based on how many chlorines you can put on carbon 2. How many chlorines can you put on carbon 2?
2.
Here's the second carbon. How many chlorines can you put on there?
1.
So we can't have a 2-2, can we?
No.
Okay, so these are the 1, 2, 3, 4, 5 possibilities, right?
So we need to look at cis and trans.
So now we need to look at cis and trans. So which one of these are possible cis and trans? 1-1, there's no cis, there's no trans.
So 1-2.
1-2, there's no cis and there's no trans.
How come?
Pardon me?
How come?
Because you need 2 hydrogens and they need to be on opposite sides
I see. Yeah.
or the same side. What about this one?
We already did
So
that
the
one.
1-3, there's actually 2 of them, right?
Mhm.
Okay. How about the 2-3? Any possibility of cis trans here?
No.
No. And then how about the 3-3? Any possibility of cis trans here?
I think so.
No. Oh, on this one?
Well,
Or
yeah,
this one? Which one were we looking at? This middle one or this one on the end?
the middle one. But never mind.
Oh, I don't think so because there's 1 hydrogen bonded here, right?
Right.
How many on the end?
2.
We don't need 3 hydrogens, we need 2.
Right.
Okay, so here is where your book has failed you, is that there is one more molecule, but it's not a cis trans. And now I'm going to draw it for you. This one and this one. This one is a Z and this one is an E. Z stands for Swisson, E stands for entigen. Entigen is kind of like a trans and Z is kind of like a cis. But they are not cis trans. And the author of this particular text is not really an organic chemist. So in his mind, this is a cis and this is a trans, and it's wrong. But you see how these two are different, but yet they're the same.
Yeah.
Okay, so let's go ahead and name these. This is going to be 2,2-dichloropropene. This one's going to be Z, and then what are we going to call this?
2, 3.
1,2-dichloro
Oh, yeah.
propene.
Okay.
Because when we have the opportunity to draw these things, we want carbon 1 to be at the left. That makes our life a whole lot easier.
Yeah.
So what is this one going to be? Trans
1, 3.
Yes. And then the rest?
Dichloropropene.
And how about this one?
2, 3 dichloropropene.
Now, you named it correctly, because one of the rules we have for numbering is you want to start numbering closest to where a substituent is, right?
Yeah.
But functional groups overrule that.
What do you mean?
Well, an alkene is a functional group. We want the functional group to start at a low carbon. So if we number based on substituents, we would start here on this end, call this 1, 2, 3, and the propene would be a 2-propene. If we number from this side, 1, 2, 3, this ends up being a 1-propene. And the deal is that you want the functional group to have a lower number, damn the substituent.
Okay.
Okay, so you didn't name this correctly because the functional group takes precedence over the substituent. Okay, what's the name of this guy?
Well, now I'm not sure, but I want to say 3, 3 dichloro.
3, 3, because the functional group takes precedence.
So it
So
wouldn't
1,
be
2,
1.
3.
So
Okay.
it wouldn't be 1, 1 dichloro.
It would if the substituent took precedence over the functional group.
I see.
Well, who wins for the naming?
The functional group.
Functional group, and this wins.
Okay.
How about this one?
Cis 1, 3 dichloropropene.
And this one's E. E what?
1, 2 dichloropropene.
So this E and Z thing is something you're going to learn in organic chemistry. And you're going to find out that, oh, yeah, they are not cis and trans. Cis and trans is very specific. 2 hydrogens, 1 on each carbon, opposite trans, same cis. That's cis trans. E and Z is when you don't have 3 hydrogens or 2 hydrogens, but rather you have different things attached here.
So
And these things that are attached are assigned importance based on their atomic number.
Oh, okay.
The larger the atomic number, the more important they are. So chlorine has a larger atomic number than this carbon or this hydrogen that is attached here. So the chlorines win, and since the chlorines are on the same side, Zwischen, which is a German word for same side.
Mhm.
And here, since the chlorines are the winners and they're on opposite sides, it's called Entgegen, which means against.
Okay.
A lot of nomenclature is based on German language because the Germans did a lot of chemistry back in the early 1900s, and they're responsible for a lot of the chemistry that we do now.
Yeah.
Okay, so here, they kind of blew it with the cis-trans thing.
I see.
There's only 6 when you consider cis-trans. There's 7 when you consider EZ. Okay, so that was number what?
36.
36. So we've done 3, 21, and 36. We've only done 3 problems.
I know.
I think we'll stop after this one.
Okay.
Elemental analysis of a colorless liquid has given its formula as C5H10. Now, they don't say it's molecular formula or empirical formula, but if you had to guess, is this the molecular or empirical?
Molecular?
Why are you guessing that it's molecular?
Because that gives us all the information.
It doesn't say molecular formula. It says formula.
Right.
So it is a molecular, but why?
I was just thinking if they gave us an empirical, how would we know what to draw?
Well, I would say this, though. We know it's a molecular because isn't this the same formula simplified?
Yeah.
Is the empirical formula the most simplified form?
Yeah.
So this has to be a molecular formula. And this has to be, this is the empirical. So we should be able to understand that without saying, oh, they wouldn't do it otherwise. Okay, for one like this, you can see. Okay, you can recognize that's either a cycloalkane or an alkene. And the reason for that is both have the formula CnH2n.
Alkene formula is, I thought it was CnH2n minus 2. Alkene.
That's
Oh,
alkyne.
alkyne.
This is an alkene.
So alkene, not alkane, is CnH2n.
Right, so alkane is CnH2n plus 2. Alkene is CnH2n, and that's for only one double bond.
Okay.
And cycloalkane is CnH2n, and that's only for one ring. And then there's alkyne, which is CnH2n minus 2, and that's only one triple bond.
Yeah. Okay.
If you had 2 alkenes, you'd have to take away 4 hydrogens.
Okay.
Okay. A chemical test to determine the class to which this compound belongs involves adding bromine. Explain how you would use this to distinguish between the 2 classes. So we're going to take a closer look at halogenation of alkanes and cycloalkanes. So if you have an alkane like C5H10 and you add bromine to it, you're going to get C5H9Br plus HBr. Now, the thing I did not tell you previously about this reaction is that it requires light. If you don't have light, it doesn't work very well. And if you're guessing that, you're going to need the light to break the bromine-bromine bond so that one of the bromines can add over here. That's exactly right. You need light to break the bromine-bromine bond. Now, we're not too worried about light being able to break the bromine-bromine bond because it's not a molecule you find in living things, a BR-BR. So we don't, luckily for us, that doesn't matter. Now, this is acid right here, HBr.
Yeah.
Now, for halogenation of alkenes, so C5H10, when you add bromine, we're going to get C5H10 Br2 and nothing else. So what are the two ways we can tell the difference between the reactions? The first way is try without light. This one's going to work whether you have light or not. This one will work whether you have light or not. So try it without light. If it works, it's an alkene. Does not work, you got the cycloalkane. Are you with me there?
Yeah.
Okay. Try it with light. Now they're both going to work if you have light. So how are you going to tell the difference? Use pH paper. Use pH paper. It'll turn red because of the acid. If it's a cycloalkane, no red if an alkene. Because notice one of the products of the reaction for alkanes and cycloalkanes is an acid. So there's two ways to tell what type of reaction you have there. The better one is light, no light. Now, how do you actually tell that you have a reaction? Turns out that this is brown and this is colorless. So here in the dark, if you add a drop of bromine to this, it turns the solution kind of brownish and it doesn't change color unless it reacts. This, when you add the drop of brown bromine to this, the brown color goes away immediately. So that's how you tell if you have a reaction. If the brown persists, no reaction. If the brown goes away, you have a reaction.
Yeah.
Okay. Okay, and that's where we were going to end. We're already been at it for an hour and a half.
Alrighty.
Actually, we can do one more. We can do 40.
Okay.
This one is fairly straightforward. These are benzene rings with substituents attached to them. And the way you name them is based on the orientation of the two substituents. So this is a benzene ring. The benzene ring has resonance. And this is called the resonance hybrid. And we talked about this before where there's p orbitals lined up all around this thing, and the electrons are in the balloon above or the balloon below for the p orbitals. And this represents the two balloons. So if you have two substituents like this is called ortho.
Ortho?
Ortho. If you have two substituents like this, it's called meta. And if you have two substituents like this that are opposite, it's called para.
Okay.
So what do you call this?
Or what is that?
That's a DR,
Ortho.
orthodox, because there's two of them, docs.
Okay.
This is another one. What's this one?
Metamucil.
Do you know what that stuff is?
Yeah.
Oh, that means you're old.
No.
Only old people know what Metamucil is. So here, we'll call this one. So what's that?
Paratrooper.
It's a paratrooper. Or you could do paradox, right?
Yeah.
But you couldn't do paramucil because there's no such thing. So how do we name each of these? Is this one ortho, meta, or para?
Ortho.
So we would write O for ortho, and then we would write chloro, nitro, benzene. Now, why did I write chloro before nitro? Is it because chlorine was at the 12 o'clock and nitro was at the 1 o'clock? And the answer is no, it's alphabetical.
Okay.
So what would this one be? Ortho, meta, or para?
Para.
So we write a P. Now there's two nitros. Are we going to write nitro, nitro?
No, probably just 2 nitro.
What's our word for two?
Di.
Excellent. Dinitro. And then what type of ring is this?
Benzene.
Benzene. And how about this last one? We have to think about what is the C2H5? 2 carbons, right?
Uh-huh.
5 hydrogens. What is that thing called?
What do you mean?
It's not ethane, it's
Methane? No.
ethyl,
Why?
because it's a substituent. If there was a hydrogen here, it'd be ethane.
Yeah.
But when it's attached to something else, it's called ethyl.
Yeah.
Okay, so what are we going to call this one? Ortho, meta, or para?
I guess it's ortho.
That's right, because they are right next to each other.
So it's an ethyl because of the 2 carbons, right?
Yeah, 2 carbons is ethyl.
So is it just
Ortho,
chloro, ethyl, benzene?
chloro, ethyl, benzene. Now, there are some names you want to know for some molecules that look like this guy here. This guy here is called phenol. This guy here is called toluene.
What is that? OH at the top?
Yep. So that's an alcohol.
Yeah. What is connected to the bottom one?
Down here,
Uh-huh.
nothing. These are molecules that only have one substituent.
Okay.
So you could actually call this ortho chloro toluene.
But what's up with the branch with nothing on it?
Well, what does that line represent?
A carbon.
No, it represents a bond.
Okay.
What's at the end of the bond here?
Carbon.
What's at the end of the bond here?
Carbon.
Okay, so what is this single
Okay.
line represent? A CH3, right?
Yeah.
And what do we call a CH3? We call it a methyl.
Methyl.
But in this case, we'd call it toluene.
Okay.
So these are two common benzene rings with substituents, phenol and toluene.
Toluene.
Toluene. You can go to Home Depot and buy a bottle of toluene. It's a solvent.
Okay.
Okay, so that's number 40, and we'll call it quits there. Thank you for asking your questions and for tuning in. I'm going to post the answers to, let's see, I recorded it somewhere.
Did you already post last night?
I believe I did.
Okay.
I
Alrighty.
will double check today, but I believe I have. But today we did 3, 21, 36, 38, and 40.
Yeah.
And as soon as it pops up in Zoom in the next hour or so, I'll post it on YouTube.
Thank you.
You're welcome. Thanks for calling in. And
Bye.
I'm glad we settled that helium or hydrogen neon one once and for all.
Yeah.
All right. Have a good day.
Bye.